Okay, so yeah, we'll make a start then. So thank you everybody for attending. Welcome to Genius Energy Lab and ground source heat pumps today and tomorrow. We're scheduled for an hour, and normally we've got 5-10 minutes at the end for questions, but I would really encourage you to ask questions as we go. Please ask questions via the chat, and Duncan will manage the chat. What we'll be doing is looking for questions and looking for the right time to ask that question for us. So if you put something in and Duncan seems to ignore it for a few minutes, don't worry, he will come back to you. It's just that he's waiting for the right time in the presentation to ask that question. I've also got some other colleagues of mine from Genius Energy Lab online, and they might answer some questions in the text. So please do look out for any answers that come in. By all means, ask questions as we go. That really does help me to tailor the content towards what you are interested in and what you'd like to hear about. Okay, so thanks again for attending, and I think we're now a couple of 3 minutes past, so shall we start away?
Yeah, start away, please, Chris.
Start away. Okay, we are recording the session, so if you do happen to miss a bit of it or have to leave early, or a colleague wants to see it, then it will be available for you. Okay. So what we're going to cover today, we're going to do a brief introduction to Genius Energy Lab, what we do and what we're about. Then we're going to talk about a case study of how we've engaged on a real project that's under installation at the minute. And then we're going to move on to the main part of the presentation, which is to talk about hybrid systems and heat networks. We'll then go on to myth busting and talk about, there's plenty of myths around ground source, and so hopefully we'll knock a few of those over today. Then a few other bits and bobs before we finish up, one on the hybridization of solar and ground source, which is an increasingly popular option for us. Touch on deeper geothermal as well, and then go into ground source as a long-term asset. So for those of you who have just joined, Chris Davidson, Chief Technical Officer of Genius Energy Lab, and thank you so much for attending today. So what are we? Well, we've been at this for over 20 years now in the ground source heat pump space. Myself and a number of my colleagues were originally in a contracting business. 2013, most of us moved on, and we have since become involved in a design-focused business called Genius Energy Lab. We're closing in on 1.21 gigawatts of systems installed. Forgive me if you're not old enough to recognise the film reference there. And what we are about is giving you specialist input to make sure your projects have got substance, lower risk for yourself, and make sure you're giving the best possible advice to your customer. Let's talk about a project in central London. As I say, it's under installation at the minute. We started on this one with some informal early engagement, and that was just a call, an email. Is a justice centre in central London with this kind of floor area a sensible option for ground source? What can we achieve with a ground source solution on that site? And that's a very common introduction to how we get involved in projects. We also don't look to charge for that type of advice. So please, please don't be a stranger. Please email us. There's email contact details below and on the last slide. So please just give us a call or send us an email. We are more than happy to provide that informal early engagement free of charge. In this instance, though, we went on to REBA Stage 2 report, and that was a desktop-based geology. At that point in the project, there was no need to go to site. It was all done off the desktop. And we did a preliminary ground loop design and system efficiency modelling to then feed into the planning process for this building. Now, it's really important to point out that even at those very early stages, we're actually using the same design process as we use for a REBA Stage 5 design. So we're not using rules of thumb. Rules of thumb are a real problem in ground source because they're always wrong, and they do tend to rule projects out that otherwise should be taken forward as a matter of course. And I'll come back to that in just a little while. So using that same design process, we then took the project forward to REBA Stage 3. Again, more ground loop design, in this instance, quite a lot of structural input because the boreholes are installed under the footprint of the building during construction. Lots of work then on project programme, cost analysis and so on. And then at the end of Stage 3, we specified some specialist test bore packages. So that's the first time that on-site analysis was required and test bores were installed. Now, it's not universally true that test bores are required. Certainly on smaller projects to medium-sized projects, test bores are just not economic and not required, so we rely on the desktop analysis to do that. On some projects, we will test the first borehole as it's installed, but on the very largest of projects, it often makes sense to mobilise the site, which is what the specialised package was all about there. Then moved into stage 4. At this point, our role starts to become more supporting project team meetings. And I see a number of our customers around the table today who've had experience of us sitting around the table, just helping to educate, to fix roadblocks and so on that might come along as a result of ground source being installed in a project. In this instance, we are still discussing whether we're going to stay client side, whether potentially we might be novated to the main contractor or novated to specialist contractors to provide oversight for the project or to continue our design services. In that regard, on those latter stages of the project, we can very much be flexible. So, don't worry about how we get involved. We're just here to help at that point. In terms of customers, lots of larger installers or installers of all size really do outsource their design to companies like ourselves. We also do a lot of work for mainstream consultants. AECOM's a big customer of ours, for example. And then there's a batch of end users who will come along to us, universities, particularly education authorities and so on, who will come to us directly to understand how we can help decarbonise their estate. So a good range of customers. Just a little plug before we move on to the main element of it, and when I say a plug, this could be very useful for you. It's a 40-page document we published earlier on in the year. It's available for download, and Duncan or Rich will put in the chat the link to this document. It will help you through the decision-making process to get to a successful ground source installation. As I say, it's 40 pages long. Even the glossary itself, lots of terms that we use in the industry, can be incredibly helpful. So I'd really encourage you to get online and download a copy of that to be your partner through the projects as they progress. Okay, assuming there's no questions in the chat, Duncan, I will carry on. Yeah, we're all fine. I just want a quick drink. Okay, so I'm not going to go into any detail about how heat pumps work, really. I'm just giving you a little bit of preface to what ground source system design is about by touching on heat pumps for just a few seconds. So if I'm asked to talk about a heat pump and describe what a heat pump is, then I'll generally say it's a box that moves heat from a cold place to a hot place. So it just does that. It moves heat from the colder source to the hotter load if we're heating the building. It actually does that by manipulating the pressure in a liquid gas circuit, and that allows that liquid to evaporate, turn into a gas, and therefore pick up energy at a cold temperature and a low pressure. It can then drop that heat by condensing that gas and dropping that heat at a higher temperature under a higher pressure regime. It manipulates that pressure by using a compressor, which is electrically driven. And there's a final part of the process, which is the thermal expansion valve down the bottom here. Now you can think of that really as a pinhole. And just like a door, a single door in a big room, it takes people time to exit that room as a result of the constriction in the door. That's exactly what it does in a refrigeration circuit. It just keeps the high pressure on one side and the low pressure on the other. It actually opens and closes in response to what's going on inside that refrigeration circuit, and the physics of what's going on inside that are actually quite complex. Really good point. If you're interested in physics and you're interested in heat pumps, have a look at what a TXV does. It really is a fascinating piece of kit. Okay, so how does that then apply to ground source and ground source design specifically? Let's start with a few little bits of terminology. The heat we are taking from the ground we call the heat of extraction. And the heat we are putting into the building is called the heat of rejection. So this side here, we are heating, we're taking heat from the ground and putting it into the building. On this side here, we are cooling, we're taking heat back from the building and putting it into the ground. And in actual fact, these systems will be one and the same, but I've drawn them as two separate systems just for clarity. So in the heating mode, we're taking heat from the ground, putting it into the building, and we're using electrical energy to drive that compressor, as I said earlier on. Now, through the forces of friction, very, very close to 100% of that electrical energy ends up as heat on the hot side of the heat pump. So it's actually added to the heat that comes from the ground. So the heat going into the building, the heat of rejection, is very, very close to equal the heat being extracted from the ground plus the electrical energy. Now in cooling mode, we are extracting heat, but this time from the building. So our heat of extraction is now in the building, and our heat being rejected is now into the ground. Again, we've got that electrical consumption, and again, that ends up through the forces of friction as heat going into the ground this time. So it's being added to the heat being taken from the building and put into the ground. So in a very real way, the electrical energy that's being consumed by that heat pump contributes to the heating going on in the building and actually hinders the cooling of the building. And so the processes of heating and cooling are not symmetrical from a ground source heat pump point of view, because the ratio of the heat extracted, the heat rejected, and the electrical energy changes. And that actually changes depending on the heat pump involved. That largely comes down to the refrigerant gas that's involved, the type of heat exchanger that's involved, the type of compressor, controls, and so on. So in order to design these systems, what we do is we tell our design software what we need to put into the building, what we will be taking out of the building in terms of heat extraction. We then have to tell it the properties of the heat pump so we get the ratio of the quantities right. And we ask it a very simple question, which is how much pipe do I need to put in the ground to ensure that the system is sustainable in the long term, given what we've got to do to the building and given the properties of the heat pump. Now, what I mean by sustainable in the long term is if we draw a graph of the temperature evolution of that ground loop in time. So this is time down here, and this is temperature of that ground loop. What we'll do is we'll start at the temperature the ground is at, and each year we'll get a little bit colder. Every winter we'll get a little bit colder. But what we don't want that to do is just continue getting colder and colder and colder. That would not be a sustainable system. We want it to level off or tend to a limit, as we'd say in maths, within the effective operational envelope of that heat pump. If we look at now at a heating and cooling system, then that graph goes in both directions. It'll get warmer in the summer and colder in the winter. And again, we don't want that just galloping hotter and hotter or colder and colder. We want it to tend to a limit, again, inside the efficient operational window of that heat pump. So that, in a nutshell, is ground source design. Given what we need to do in the building, given the properties of that heat pump, how much pipe do we need to put in the ground to make it sustainable in the long term? Now, I've just drawn it here as a borehole system, a closed-loop borehole system, and I'm going to define exactly what that is in a little while. I'm also going to talk about the other types of ground loop that we have available to us. But in the main, for the first part, I'm just going to talk about closed-loop boreholes. Okay. So let's look at how that is applied to a commercial building. Duncan, did you?
Yeah, I was just going to add into that. I always find it very useful to understand why it tapers to a limit rather than stops getting colder and colder. And it's also you describe it beautifully often by showing the inflow of energy increasing as the temperature difference gets bigger.
Exactly. So if we imagine our borehole ground loop is a big lump of ground, big cube as I've drawn it here, or rectangular cube, whatever you call that, of ground. We are decreasing the temperature inside that loop if we've got a heating dominated system. So we're pulling the temperature down. What's going on here, of course, is we've got the temperature out here in the general mass of Earth, and as a temperature difference is established between the ground out here and the ground inside our ground loop, then energy is naturally going to flow in. Heat flows from the hotter to the colder is the basic physics involved. The bigger the temperature difference, the quicker that heat flows in. And so that's how you get this shape of graph. The bigger the temperature difference, the more that graph's going to curve and flatten out until you get to a point where energy in equals energy out, and that's a sustainable ground loop. Great question, thanks, Duncan. Okay, so how do we then apply that to a typical commercial building, and what considerations do we have to go through in order to have a successful ground source installation? What I've got here is a typical heating and cooling system in a commercial building. So what I've got is one heat pump cooling, so that's putting heat into the ground loop, and I've got a couple of heat pumps here heating. They are taking heat back out of that ground loop again. And so right away you can see we've got energy recovery going on inside that ground loop in that header there. Now there are quite a number of heating and cooling systems that will give you that instantaneous heat recovery. But the real magic of ground source is we can extend that heat recovery interseasonally. So we can actually recover heat between winter and summer in the ground. Now that is critically dependent on the geology. So the geology isn't really just important in terms of how much native energy can it give you, i.e. what's the conductivity of that geology. We'll have different layers of that, and that geology will have different layers of conductivity. So we might have a poor conductivity on the top here and a better conductivity down here. So it might be poor there, better here, and then better again at the bottom. We might also have groundwater involved in it. So for example, we could have some moving groundwater here, which is washing through the system. Now, if we're relying on that level of ground to store energy, you can see that that groundwater is going to be moving that energy away. So we not only have to understand what the native properties of the rocks are, but we've got to understand the hydrogeology as well, i.e. what the groundwater is doing. So we need to really understand intimately what's going on in the ground. And that's what we mean by desktop geological analysis. We can analyse through the borehole records we've got available to us and the geological materials we've got available to us, which we're really lucky in the UK, sorry. We've got perhaps the best in the world geological information available to us. So from the desktop, we can assess what we've got in the ground and work out not just the thermal conductivity and the temperatures involved, but also what that hydro environment, what that water environment is going to be doing as well. Let's now look up into the building. This is what we call a sliding header. So what we've got here is we've got one heat pump cooling, as I said, two heat pumps heating. So these valves here would be shut. These valves will be open. And let's say we're now moving into the summer, as we hopefully are at some point. What we would be doing is more cooling. Therefore, we'd shut these two valves, open up these valves, reverse this heat pump, and we've now got two heat pumps cooling and one heat pump heating. And we can go all the way to one direction, all the way to the other, hence call this sliding header. It's really important to understand, though, that we're not just sizing the system on a peak load. We need to understand the nature of that loads, and that's not just for the ground loop model. We need as a minimum monthly load profile breakdowns for a ground loop model. Ideally, we'd have hourly, and we are increasingly working on hourly models, but monthly is a minimum. And we not only need to understand that in terms of modelling how much pipe we need to put in the ground down here, but also to understand the nature of those loads so we can select our heat pumps. We've got to select the appropriate number of heat pumps with the appropriate number of stages so that we can accurately match those loads. And thinking of a number and doubling it isn't helpful as far as sizing heat pumps are concerned, like you used to do with boilers. If we've got a 300 kilowatt load here and we put 500 kilowatt heat pumps in there, we're going to be grossly oversized for the load. So we're really going to want 100 kilowatts or close to it, so we're really accurately matching that loads in the system. We've also got to understand what can these systems turn down to, because that 300 kilowatt peak heating load might actually translate to a 10 kilowatt heating load, and how do we cater for that with big 100 kilowatt heat pumps? And to illustrate that in a little bit more detail, let's just think of a common mistake that's made in this regard. Let's say we've got a 10 kilowatt. That's helpful. The fire alarm hopefully isn't about to go off. Let's say we've got a little 10 kilowatt server room load here. So it's just cooling all year round. And let's say we've got those 100 kilowatt heat pumps here. Let's say we're in the dead of winter. All these heat pumps are heating. And so to satisfy that 10 kilowatt cooling load, we've now got to bring on that 100 kilowatt compressor and deliver that 10 kilowatt cooling load. Now, think of that as you're driving along and forward in your car, you're now reversing it and accelerating violently in reverse. It's not going to be good for either fuel economy or the longevity of your car. Exactly the same is true for a heat pump. If you're reversing, then turning on that big heat pump to satisfy that relatively small load, then it's not going to be either efficient or good for the longevity of that heat pump. So once you understand you've got that 10 kilowatt cooling load all year round, you might just dedicate a little heat pump to it, connect it up to the ground loop so it's injecting heat back in, and that's just going to look after that 10 kilowatt server room load all year round. So that illustrates the type of considerations that you've got to go through when you're looking at the geology, the heat pump selection, and how you deliver that into a building.
Lovely. Chris, could we just expand on how confidently we can assess the geology from the desktop? We've been asked a question by Yash regarding relating to the geology and how we can be so confident from the desktop when there are no research papers on a given location.
Okay, thanks, Yash. Great question. So we've got a huge wealth of knowledge to fall back on. And in most cases, actually, we will be going and installing systems or designing systems that will be installed without on-site physical testing. And that's just because it wouldn't be affordable to do that testing. So we've got to risk assess what's our knowledge base like, and what does that then say about the geology and the risk associated with a high or a low conductivity that we're actually going to get on the system. So What we'll be doing, if we've only got desktop information to go on, is do we have local tests available to us? And we've got well over 300 local tests available to us that we can use in our analysis. And also, what's the variability likely to be in that specific ground condition that we are looking at? Some ground conditions are very, very precise in terms of, or we can be very precise in our desktop assessment of conductivity. Other ground conditions, we've got a bit more variability on it. Now, what we don't do is take a worst case on everything. What we'll do is take a worst reasonable case. So we're not going to look at the real outliers of data and expect that to be typical of where we are, unless we've got very good reason to do so. We're going to be looking at a worst case reasonable, and that's where we tend to fall down, where we tend to come down on the side of geology. But it's very different depending on the ground conditions we're looking at. So, for example, the chalk, which is under the southeast of England, it's the same chalk you see at the White Cliffs of Dover, and that's got quite a variability in its conductivity, depending on the environment in which that chalk was formed. So if that chalk was formed in a nice clean sea, the little creatures that were living in it died, their bodies came to the bottom, and it would form a limestone, the lime being the skeletons of the creatures involved. If there was quite a bit of murk in that water, so maybe it's a river estuary that it was in, then there'll be quite a lot of particles of clay, for example, in that, and that will reduce that conductivity. So if we've got chalk, then we will be putting a lower conductivity on our desktop assessment than perhaps we would be expecting if we did a test. Hopefully that somebody gives you an idea about the level of detail we go into. We will put our PI cover on a non-verified conductivity, which I guess gives you the confidence that you need in the system, but on larger schemes certainly we'll be doing testing.
With regards to the different layers, we can be confidently accurate to the nearest meter for the thicknesses of those different layers, because there are literally tens of thousands of historical borehole records going back 150 years that we can access.
Absolutely. And then, you know, if you go up to the northeast of Scotland, where I'm from, and people just haven't been drilling so much because there's not so many people living there, then you've got more uncertainty than you would have in London, where there's, you know, thousands of holes in every square mile. Great question. Thank you very much indeed. Okay, so let's talk a little bit about how we would deploy these types of systems. I'm going to talk about a district heat network servicing some apartments just for a few minutes. I'll come back to other types of systems in a bit, but the principles I'm applying here will apply to residential as well as commercial buildings. So let's look at a conventional district heat, central plant district heat network fed by ground source. So we've got some plant down here, we've got heat pumps in the basement, delivering heat up a high temperature, well insulated riser, which is then going into a heat interface unit in each dwelling. And that heat interface unit will be delivering domestic hot water. Let's say it's doing that at 65 degrees C, and it could be delivering space heating down as low as 35 degrees C. But we've only got one riser, we've only got one mechanism for taking that heat up the building. So we've got to deliver heat at that higher temperature. That's the only option we've got. And so we are delivering heat at that 65 degrees C. Okay, we are therefore running that temperature. We're running our heat pumps at a higher temperature. Now, the thing about heat pumps is that the higher temperature we are delivering off that heat pump, the less efficient or the more electrical energy it's going to be consuming. Now, the best way of thinking about that is if I go and climb a small hill, I'm doing less work than if I'm climbing a high mountain. So that heat pump and climbing a small hill to say 35 degrees is doing less work than climbing up to 65 degrees. Okay, so we are compromising that space heating efficiency, which could be done at that lower level as a result of delivering that heating at that higher temperature. Okay, so we've got a compromise in efficiency because we've only got one riser to work with here. Let's contrast, before I leave the central plant solution, the run costs of this system can be billed as a kilowatt hour of sale agreement. And I'll come back to that in a moment because it could be critical to the economics of that system. Now let's look at a distributed plant model. So right away we can see we've got no plant here in the basement. We don't even have any pumps. And that's one thing we've pioneered in the marketplace, is getting rid of those central pumping arrangements that were previously thought to be required. We've now got heat pumps in each individual dwelling, and those heat pumps can be delivering heating, domestic hot water at that 65 degrees. and then they can turn off at that higher temperature and go to a lower temperature to deliver the space heating at 35 degrees. So we're now not compromising that space heating efficiency in order to deliver that domestic hot water. We could also be cleverer. Again, we could reverse that heat pump just as we did in the commercial building and deliver cooling, let's say 6 to 12, which would be typical cooling temperatures. Or we could even use that ground loop directly to do that cooling as well. However, there's a contrast now with the electrical energy consumed by that heat pump. So that electrical energy is entirely isolated within that apartment. And that electrical energy is a regulated quantity. And so the tenant in that apartment can buy that energy from whomever they please. So there's a commercial difference between the sale of heat agreement here and the electrical consumption. Now, what you could do is you could build an access agreement, for example, to build the use of that ground loop. And there are increasingly models allowed to do that. But we've got some contrasting engineering benefits and commercial benefits to the two systems. Economically, efficiency-wise, then almost always this one will be the more efficient system because we're not compromising that space heating efficiency to deliver that domestic hot water. However, as I said a minute ago, that sale of heat agreement might be critical as far as delivering that heat network or paying for that heat network in the first place. So we've got quite different commercial and technical arrangements for the two. In terms of installed costs, when you take everything in the round, they are very, very close to identical in terms of cost. We did a feasibility study some time ago now, and the system cost was about £4 million, and it was £4,000 difference by the time you took the two into consideration. So they can be very similar installation cost-wise, and really it comes down to more the commercial arrangements as well as the commercial and technical arrangements, in which case which is more effective for that particular project.
Whilst you're on that slide, can you use that slide to demonstrate some of the tricks we can play in hotter climates to manage the ground loop's temperature overnight via dry air coolers, for example, when it's massively cooling dominated?
Let's actually use this slide here. So let's say we've got a massively cooling dominated system. So throughout the year, we're doing more cooling than we are heating. Then what we can actually do is, if the buildings are off, it's not being operated, we can put a dry air cooler onto this ground loop, and it's got some fans in it, and they will blow heat air over a coil. If you're not familiar, a coil like a radiator in a car, and that will then allow us to exhaust heat out of that ground loop, particularly overnight. The benefit of doing that is, of course, the air temperature overnight is that much lower. Particularly in hot climates, desert type climates, you might be 30 degrees, 40 degrees in the day, and even then your air temperature is going to drop drastically at night. And so we can pre-temper, we can cool that ground loop down for the next day's operation. Think of it another way, we're hiding away from the sun, and we are using the dark sky and the cooler air at night to cool that ground loop down for the next day's operation. So that can be a really good option in very, very hot climates.
Thank you.
Thank you. That's a great question. Okay, so let's just talk briefly about the hydraulics of these systems and diversity in heat networks. If we connect lots of buildings together, I've just thrown it 6 houses here, could be 6 commercial buildings, doesn't really matter. We can assume some diversity on that network. So we can assume that not all these buildings are running at the same time. Now, what that means is, because we've got that diversity, we might be able to save a bit of ground loop. We might need some less boreholes to do the same job. But on the other hand, the water that's required for all those heat pumps has to be accommodated in the header pipes that transport water from the buildings to the ground and back, and therefore these pipes get bigger. And so there's a penalty to pay there in terms of pipe sizing and therefore installation cost. We could take the opposite view and break this heat network up. And here's an extreme example where we've got one borehole between 2 dwellings here. Now, obviously, we can't take the same level of diversity in these networks. If you're familiar with diversity, if not, have a look on Wikipedia for it. There's some good definitions, although the definitions of diversity in ground loops are really not that well put out there. We've got definitions internally that we use. Let's break this network up, 2 dwellings per one borehole. So in actual fact, the collector here, the bit that's doing the work, the thermal transfer, could be bigger than the header pipes. So there's two contrasting options again here, and in reality what we do is a mix of the two. So this again is a contracting project that we did a few years ago now at Park Erin in Wales, 250 odd houses. And if I zoom in on this little crescent here, we've got 5 boreholes feeding, I think, was it 10 dwellings there? And that's one heat network in this overall development. Let's look now at array 28 and 29 here. 28 and 29. Array 29 is a couple of boreholes. Array 28 is 4 boreholes. And those 4 boreholes are feeding those dwellings and 2 feeding array 29. Now, while those are not hydraulically connected to each other, they are actually close enough to each other to be in thermal contact. So when we're designing a system like this, we can't just look at each individual dwelling. We've got to think about how those individual arrays interact with each other. And so that gives you a snapshot of how we do the design, both hydraulically and space dependent. On a system like this, what we actually do is we plot an imaginary XY axis down the bottom here, and we actually plot the coordinates of each individual borehole off of that. And so the software is taking into account the spatial arrangements, not just in 3D for the depth, but also in an XY plane as well. Any questions coming in on the chat there, Duncan?
No, we're answering as we go, pretty much.
Excellent, good stuff. Okay, so let's now extend this into a mixed use development. We've got some consultations underway at the moment for heat networks, some about the consumer experience for heat networks and some about heat network zoning. And that looks like it will allow local authorities to declare a heat network zone. And in those heat network zones, there will be some kind of compulsion to connect to the network. And ambient loops or 5th generation heat networks, by the way, 5th generation heat networks is a hotly disputed term. A lot of more conventional district heat people think that there is somehow some arbitrary minimum temperature in this. So it might be 6th generation, doesn't really matter. Anything that's operating at something around ambient temperatures is what we're talking about. Now, if you go along to a supermarket and say you're a lovely source of heat supermarket, would like to recycle that heat and put it into some houses that are being built alongside, they'll probably see that as risk. They'll probably see it as too much hassle and they won't be particularly interested. But with this new heat zoning legislation, we might be able to go along to that supermarket, reduce their cooling costs, and it can be a dramatic reduction actually in cooling costs, and inject heat into that ground loop. Then take that heat out into those dwellings or office buildings, whatever. And again, we're extending that heat recovery interseasonally, which, as I say, is the real magic of ground source. We can go further than just connecting buildings together. We can connect these heat networks together. So 5th generation heat networks or ambient heat networks could be connected to previous generation heat networks or connected to each other to allow heat simply to flow between the two and enhance efficiency and increase diversity between those heat networks. We can also take heat from a waste to energy plant, a combined heat and power plant, a data center to just inject heat. And again, the benefit of these low temperature heat networks in heat recovery is we can recover heat at any temperature, really. So we can recover heat without using compressors to do so at very, very low energies, very low temperatures, sorry. Okay. So I promised you earlier on I was talking about vertical borehole systems. So let's talk about what a vertical closed-loop borehole is. So these are very simple in construction. They tend to be an open hole drilled in the ground, and they tend to have a single U-tube of polyethylene pipe put inside them, through which we get a continuous circuit, a closed-loop circuit. So it's the same water throughout that life of that system. That water is treated with an antifreeze and a biocide to ensure it remains healthy and doesn't freeze throughout the operation. The borehole is completed with a cementatious grout material, and that cementatious grout material stops anything getting down that borehole, polluting an aquifer potentially down there, and it also gives us thermal contact to and fro with the ground around it. Diameter of these boreholes is typically 150 millimeters in diameter, and typical depths somewhere between 100 and 300 meters deep. Okay. There are other closed-loop options available to us, principally being horizontal trenches, which are just trenches dug in the ground. In the UK, we tend to be 1.5 meters deep and 1 meter wide, and I tend to like these what's called 6-pipe trenches, which are straight loops of pipe put up inside the trench and buried. You'll often see in magazines coils of pipe slinkies, which tend to be okay for smaller domestic systems, but anything commercial or multi-residential, schools, for example, tend to have these types of systems. We can go with a horizontal straight pipe trench like that. Space, obviously, is more required for, more space is required for horizontal trench systems than for vertical borehole systems. There are other types of closed loop available to us. If we've got surface water like this, we can put heat exchangers in the bottom of that body of water, and we can take heat out of that heat exchanger or put heat back into that heat exchanger. And provided we exchange a similar or lower amount of heat with that water, the natural heat gains and the natural heat losses from it, then we've got, again, that sustainable system. The main heat gains are solar gains, and the main heat losses are actually via evaporation. Now, these can be very, very powerful systems, and at scale can be even powerful enough to the point of economics, where it's worthwhile including some lakes or ponds and so on in a landscaping for a big house or even a multi-residential system. It can be combined with sustainable drainage, for example. So they can be a really powerful way of accessing closed loop systems. There is an alternative to closed loop, which is open loop. Now, I've drawn it here using water wells. So we're taking water from the ground, we're running it through some heat exchangers, and we're putting it back into the ground again. These boreholes for water wells are much, much bigger in construction than the closed loop alternative. They could be up to a couple of meters in diameter, more commonly 600 mil, that kind of thing, but up to a couple of meters. They can be typically 100 to 150 meters deep, and they've got some serious construction in them. So they could be lined in steel, stainless steel. They could have some filtration and packing involved in them. They've also got pumps down there to take the water up through the heat exchangers and back into the ground. Now, as for clarity in this drawing, I've drawn the two boreholes very close together. In reality, you need about 100 meter spacing between the two to ensure that you're not getting a short cycling, where the water we're putting back into the ground is just immediately heading into that water and blending with that water coming out of the ground. Imagine you've got a heating dominating system, that water is going to get colder and colder. It's untreated water, and so it's not got antifreeze in it, so we can't mess around with freezing point, or else we could pop heat exchangers and so on. The other point about it being untreated water is the water quality can be variable, and the water quality is the main factor in how often we need to maintain a system like this. So maintaining the pumps and the heat exchangers. In London, where the water in the chalk aquifer under London is very clean, we could be looking at 10 to 12 year replacement or maintenance cycles on these heat exchangers and pumps. In other aquifers up in the north or in coal mine workings, we could be talking about monthly maintenance on these items. So it does vary tremendously. The other thing to be very much aware of when you're talking about open loop systems, so you're taking water from the environment in a river, lake, the ocean or so on, is you almost certainly will need some licensing for that. And that licensing process can be expensive and protracted. It can take a year to get the license required for these systems, for example. Okay, so that's closed loop and open loop. What I would say about this in summary is open loop is a brilliant technology, particularly in city centres, where the ground loop, if you like, is a very compact solution. But if you can do closed loop from an ongoing maintenance and from a licensing point of view, then really, if you can technically and economically do closed loop, then that almost certainly is going to be the better solution for you. I'm not saying open loop's a bad thing, but you just need to go into it with your eyes open. So finally, before I get into myths, oh, sorry, I've got one more slide to talk about before I get into that system. Let's talk about the hybrid of ground source and solar. This is an increasingly popular option for us. Let's think about it. Schools, we're doing a lot of decarbonisation in schools projects at the minute. The top of the hierarchy, as far as the Department for Education, is ground source and photovoltaic. That's a great decarbonisation solution. And there's a hybrid there, naturally. The photovoltaic generates electricity and the ground source consumes electricity. So we've got a hybrid, pretty trivial one. You know, one produces the fuel of the other. And there's not anything fancy about that hybrid. You just put electricity into the meter and take electricity out. More interesting, though, is if we've got some thermal elements to that photovoltaic array. So I've drawn it here as a PVT, could be separate photovoltaic. It could be a thermal array alongside, or as I've drawn it here, a combined hybrid PVT panel. Now what we're doing there is we're taking solar thermal energy and we're injecting that into the ground loop. So what we're doing is we're recharging that ground loop battery. We're putting heat back in. Now that can have several effects. One, it might mean we need less borehole overall, but it certainly means that we're going to increase the efficiency of that ground source system. So it's a real win-win. And it even goes beyond that, because in cooling that PV panel, by taking that heat away from the back of it, we are also increasing that electrical generation. And the trials we've got and the working systems we've got, we're increasing that electrical generation by about 25%. So it's a win-win. And then goes further again, we're also increasing the longevity of those PV panels because of that cooling effect. So we've got a real lovely hybrid, which gives us benefits in all regards. Test system we've got underway that we've had going for a longest period of time, about 4 years now. We're improving the seasonal COP, and I'll come back to that in a minute, from your typical heating only system, 3.5 to 4 for a ground source system. We've actually getting a 5.5 seasonal off of that system, and I'll come back to COPs, as I say, in a second. Another technology that we're increasingly involved in is this medium depth or deeper geothermal. Talking about depths between sort of 500 meters to 3 kilometers down here, much deeper than the 100 to 300 meters we're typically working at. Because we're going deeper, we'll get more off each borehole. The economics of this are up for grabs at the moment, yet to be proven, but we are very hopeful that this type of technology will allow us to address more compact, more restricted sites, for example, in the future. So just mention that. And then finally, bringing all of what we've talked about together in a hybrid system. This has been up and running for over 15 years now. It's a building called One New Change. If you imagine standing on the dome of St Paul's Cathedral and looking east, it's at your feet there. It's 3 or 4 layers of shops and restaurants, then 3 or 4 layers of offices with a lovely rooftop restaurant at the top. Highly recommended, particularly in the summer. Great place to be. The brief on this building from Landsec, who are the building owner, was to do as much as we possibly could with the geology available to us. So we looked at the building and we looked at the piles of the building, and they're unusually deep and big piles, so they're about 45 meters down into the London clay. Now, the London clay is a low conductivity ground condition, but it's also a really excellent thermal store. So we put pipes into the piles of those buildings, and that is our interseasonal energy store. We've got other things we can do with that ground loop as well. We can use water wells, which are using the water in the chalk here, and we can temper that ground loop using that water in the chalk. It's a bivalent system, so we can schedule loads on and off as well. So we can take cooling and put heat into that loop. We can use it for heating to take heat back out of that ground loop. And the name of the game here is, unusually, most systems, most ground loops are designed and left to operate on their own. What we're actually doing is actively managing the temperature in this ground loop in order to optimize the efficiency of the system by scheduling the loads on and off and utilizing that water wells. Now, the magic number for the particular heat pumps involved here is 20 to 25 degrees. So we're actually managing that ground loop temperature in that 20 to 25 degree regime. And that just happens to be the point at which the cooling efficiency and the heating efficiency crosses over for that type of heat pump. So we're maximising both heating and cooling efficiency. Now, the last time we got some numbers on this, we're achieving a seasonal COP of 6.8 in heating and 4.8, sorry, 6.8 in cooling and 4.8 in heating for that system. So potentially one of the most efficient buildings in operation in London today.
Well, before you go on to myth busting,
yes.
What is your opinion on the recent decision to increase the capacity limit under the boiler upgrade scheme from 45 kilowatts to 300 kilowatts to enable larger shared ground loops to be eligible for support?
Well, as a company who designs a lot of shared ground loops, then it's a great idea. I guess it depends on whether you see the boiler upgrade scheme being intended for individual dwellings, and I completely get it if your view is that by increasing it into multi-residential schemes, then we can access more and get more systems installed. Whilst you could take the view that it's a scheme about individual domestics. Personally, I don't. I think that, particularly when we're doing the multi-residential, we're talking about alleviating fuel poverty, those kinds of things. So it can be a key enabler for all of that. So yeah, I'm very much for it.
Thanks, Chris.
Got into lobbying there for a second. Yeah. So I must confess I do a lot of lobbying on behalf of the industry, and part of the decision was influenced by what we've been talking about as the Ground Source Heat Pump Association. All right, myths. There are plenty of myths around ground source, and so let's bust a few of those. People often talk about the ground freezing. We do run at negative temperatures in ground loops, and there's nothing wrong with that. But if you are seeing adverse effects at the surface or in structures as a result of that, then you've just got a badly designed and inadequately designed ground loop. So we don't freeze the ground. We do run at negative temperatures in ground loops. And as I say, there's nothing wrong with that. So let's deal with that one. There's lots of reasons why you can't do ground source that are said in lots of reports. And we get these reports day in, day out from from consultants, contractors and so on, saying we can't do ground source because we've got hard rock, we've got soft rock, we've got archaeology, we've got the wrong type of building, we've got an R in the month. You know, lots of reasons why you can't do ground source. All of them nonsense, quite frankly. In the main, ground source is universally applicable. There are reasons in some limited cases why you can't do ground source, but they are an awful lot less than is stated. So can't do ground source, you know, very seldom is the case. Let's talk about reliability and complexity. One of the things mistakes that a lot of people make when they get involved in ground source, first of all, is to overcomplicate things. By keeping them really simple, you can not only enhance the efficiency of the system, but it actually enhance the reliability of the system as well. So you've really got to be careful when you're designing reliability into the system, not to overcomplicate things. And similarly, ground source can be designed to be more reliable than actually any other heating and cooling technology out there. So with the right design, we can tick the boxes of reliability and complexity at the same time. Talked about archaeology. There's absolutely no reason why in a system, in a site with archaeology, we can't do ground source. The top few meters that are archaeologically interesting, we're through that very quickly, and you know, an archaeologist can be on site during that excavation, so we can do that absolutely. One thing to be careful of is what I often call it is miracle loops. So people come along to us and sell us this new construction inside a borehole that's going to give you 6 times more than anything else in the marketplace. What I can tell you is that almost always the determining factor for how much you can get out of a borehole is the ground, not what's inside that borehole. So just be careful. Yes, in some geological circumstances, some kind of fancy loop can give you more, but in most cases, it's the ground that's the determining factor. So just be careful with that one. COP and seasonal COP is a much vexed topic, and people are using COP, coefficient of performance, which is how much heat do I get at a specific condition divided by the electrical consumption. Now that specific condition for air source is 7 degrees on the source and 35 degrees on the load. And for ground source, it's 0 degrees on the source, 35 degrees on the load. It's not an equal playing field. That's more like an average air temperature in the UK, and that's a minimum water temperature for a ground source in the UK. And so it's not a fair playing field. So if you're comparing air source and ground source or other types of system with COP only, you're not doing justice to the technologies. You've got to look at seasonal COP, which is the annual heat delivered divided by the annual electrical consumption. Now, from a ground source point of view, that's pretty easy to work out, because in the design software, if you give us hourly loads, we can give you that COP by the hour and therefore give you a very accurate seasonal COP. For air source, a bit more complicated. You've got to look at regional air temperatures to get the variability in the source temperature, but you've also got to look at humidity. In the UK climate, which is never that cold, so the air dries up, it's always this damp and cold that we get during the winter, you'll get condensation forming on the coils of air source, and therefore that will freeze because the coils are cold, and you need to defrost. So you've got to consider not just the temperature, but the humidity of the air, and that's something that ground source just doesn't suffer from. So please don't use COP, use that seasonal COP. Life cycle costs are absolutely everything in ground source, and you've got to really look beyond the initial cost. If your only interest, or your client's only interest, is installed cost, probably ground source isn't for you. I'll come back to how that might not be the case in just a second. But if you're looking at life cycle costs, anything beyond that initial year, then ground source really starts to come into its own. And you know, in life cycle considerations, 8 to 10 years, ground source could be half the cost overall of air source. Space required is often overstated as well. I've seen a business park system, which is a multi-megawatt system, rolled out on the basis that you couldn't fit enough horizontal trenches in. You know, that you're never going to do that with horizontal trenches. It's always going to be borehole. So come to us. We'll certainly help you out with that space required, and please don't use rules of thumb. Back to the question a minute ago about the boiler upgrade scheme, and this is really where I'm coming from with that question, is if you start to do ground source on a house-by-house basis and expect to turn it out over a massive percentage of the houses in the UK, that's a hugely expensive if you do it individually. So if I put a borehole in for my house and then a couple of years later my neighbour comes along and puts a borehole in, that's a hugely expensive undertaking because of the mobilisation costs for getting drill rigs to all these houses. But if you start to look at the world on a street-by-street basis, on a town-by-town basis, as we're doing with our partners at Kensington Utilities, for example, then you've got a hugely compelling proposition. And it's much more like the installation of gas pipes was back in the 60s, 70s and 80s. Gas was rolled out not on a house-by-house basis, but on a street-by-street, town-by-town basis. And that's increasingly how we're looking at ground loops as an infrastructure asset. And that brings me to the final slide, the economics of ground source. These are really being turned on their head at the moment because of that infrastructure asset, that infrastructure investment. So companies like Legal & General, for example, are investing in the space heavily because of the ownership of that long-term infrastructure asset. They're not looking at a return year one or year two, they're looking at ownership of that in the long term, just like gas pipe, just like water pipe, broadband infrastructure, electrical cabling, and so on. So by looking at it in that way, we can go along to a developer who might be building a couple of thousand houses, and from a planning point of view, they're maybe trying to get away with direct electric because that's the cheapest install for them. Good luck with that, unlikely to get through planning. So they're probably looking at air source, and that's, on the face of it, the cheapest installation for them. But when you look at that third-party ownership, just like gas pipe, just like water pipe, of that ground source infrastructure, and even third-party ownership of the heat pump itself, then ground source becomes the less expensive solution overall, even less expensive than direct electric potentially. So again, the economics of ground source are changing dramatically. Okay, over to questions.
We've got one in the chat. Do you suggest horizontal in hot climates?
Horizontal can be useful in all sorts of climates, and there's some subtlety involved in that. The more extreme, so horizontals, unlike verticals, are much more seasonally in contact with the air above. So you'll see at 1 meter, 1.5 meters down, you'll see a winter summer variation in the temperature of that ground because it's closer to the surface. When you're talking about a few hundred meters down, you just don't see that interseasonal variation. You get longer term variations, you know, over hundreds of years, but not that annual variation. And so at a shallower depth, horizontal will be in closer proximity to the air temperature above. So very cold climates, I did a system for a church in Siberia many years ago, and we were many meters down before we could get a stable enough temperature to make ground source make sense. Similarly, in very hot climates, then you are into that interseasonal variation. The downside of it is, and if you think about what I talked about earlier on, that day in, day out variation of hot in the day, cold, hot in the day, cold at night, you don't quite get as much of that filtering down to that 1.5 meters. So the chances are you're not getting that benefit of that colder temperatures at night. It will be more stable than the air temperature, but it's not going to get that benefit of that drier, cooler type overnight cold. So there's quite a lot of subtlety involved in that one. Great question. Thank you.
Cool. That's it for the current questions. If anyone else has any questions, please feel free to type them in the chat. Alternatively, I can put my email address into the chat if anyone has any follow-up questions that they think of at a later date.
Yeah, I've just noticed a typo there. It's not a hybrid email address web site there. It's geniusenergylab.com, not /com. So I'll fix that. But yeah. Okay, so that remains to be seen. to be said then. Thank you very much indeed for your attendance today. It's great to see so many people interested in us and the technology. If you've got any questions, please do contact us at the email address, the phone number there, or Duncan's email address is in the chat there. We're more than happy to answer any questions. If you've got any specific projects to look at, we're not going to look to charge you for initial advice. That's absolutely fine. Please don't be a stranger and come to us with any queries you've got.